Hi, I am Dr. B. Ravi Kumar, Associate Professor, Department of ECE, Institute of Aeronautical Engineering. Today, I'm going to explain about encoder and decoder. First of all, let us see encoder. What is encoder? Encoder is a combinational circuit that converts the binary information from 2 power n input lines. Basically, a combination circuit which requires a 2 power n lines into a n line bit outputs. For a simple encoders, it is assumed that the only one input line is active at a time. As an example, let us consider octal to binary encoder. If you see this figure, it is an octal to binary encoder which takes 8 input lines and generates 3 output lines. In general, if you consider that inputs must be 2 power n and output must be n, or the input these are represented by a different elements which will converted into a binary information. The encoder is most probably represented by 2 power n input lines to n output lines. This 2 power n may be maximum or which is equal or less than or equal to of the 2 power n lines, which is depends on the combinations of the n lines. And this encoder may be used with this conjunction with this, like BCD to binary conversion or binary to BCD conversion. So sometimes we use this type of encoders. This is the truth table which explain. The truth table means this is the relationship between input variables and output variables of a particular circuit. In this particular circuit encoder, let us take, there are different types of encoders like 4 to 2 encoder, 8 by 3 encoder, 16 by 4 encoders. Let us consider octal to binary conversion encoder, for which the 8 inputs and 3 output lines. While preparing the truth table, we need to take that number of inputs and number of outputs. And also, if you want to make this kind of combination circuit, we have to follow design steps. The first step is problem define. Problem definition, and second step is finding the input and output variables, and third step is assigning the variable names for IO, and fourth step truth table, fifth step Boolean function, minimized Boolean function, and the sixth step draw the logic diagram. Based on these steps also we can see that like a fourth step truth table. So we have the problem that designing the encoder, understanding the encoder, and we, for example, if you take the octal to binary information, binary encoder, that inputs must be, octal means 8 number of inputs and output must be 3. So we can assign 8 inputs and n inputs and 3 outputs, and assigning the names for input and output variables. In this case, I would like to assign the names of D7 to D0. So I am putting in the table, and X, Y, Z are the names of the outputs in the encoder. So coming to the truth table, the relationship between these 8 inputs and 3 outputs. These are the 3 outputs. These are the 8 inputs. So if you see this table, generally in the truth table, for the input and outputs, we have to take the combinations of how many variables are there in the input. But in this case, so it's not possible to take 2 power 8 possibilities, take the inputs and then corresponding what is its corresponding output. But according to the definition of the encoder, so among 2 power n input elements or input lines, so at a time one input is active and that its corresponding output need to be generated. So based on that concept, so at a time one input is active means the remaining all are inactive. So in order to reduce all the combinations of 2 power n, we consider what is those particular input combination is active and remaining all are zeros. So we can consider all that combination. So in this case, if you consider remaining all are zeros, only D0 will be active. The input D01 is active. So remaining all inputs are zeros. What will be its corresponding output in the encoder? Its corresponding output in the encoder is, so whatever the logic one which under input combination, input element D0, so its corresponding binary number is, for D0 means 0, its corresponding binary value is 0, 0, 0 in the 3 variables. So that's why I am mentioning here 000 in the first row. Similarly, what if a second input is high, remaining all are zeros? Then the D1 is only is active. Then encoder which encoding the binary information for particular this D1 only. That means its corresponding one is like 001, where X is the lower least significant bit. Likewise, we can make the second row, take the all zeros and only D1 is 1, remaining all will be zeros. So when D1 is only active input, then its corresponding binary information is 001. So that's why we can take 001. Similarly, we can make the table for D2 active, its corresponding binary information 00010. D3 under D3 is equal to 1, remaining all inputs are zeros. Its corresponding encoding output is 0111. Indirectly, that encoding output means its corresponding binary information. So D4 is only active, its corresponding output is 100. And D5 is active, its corresponding output to encoder output is 101. D6 is only active and 110. And D7 is active, its corresponding outputs are 111. In this way, we can make the truth table. For 8 combinations of inputs, only at a time one input is active, its corresponding binary conversion or encoding of its corresponding output. Now, the next step in the design procedure is Boolean function from the K-map, or by inspecting the truth table, direct inspection of the truth table. So here, it is not possible to take the 8 variable inputs and find out the minimized Boolean function for x variable x, y, z. Instead, we can go with the inspecting method. By inspection of this truth table, we can find out directly for this what is the Boolean function for x, what is the Boolean function for y, what is the Boolean function for z. So if you take this one, the truth table, in this truth table, what is x? So here it is the x nothing but only 4 ones in the output column. What is its corresponding binary, like octal element? So here it is D4, D5, D6, D7. So what is its corresponding Boolean function for this x? The Boolean function for x is equal to, directly we can write down the Boolean function. So when D4 input is active, you will get the logic 1, or D5 is active, you will get the logic 1 in the x, or so in this case I am treated as x is the MSB bit. So D6 plus D7. So these are all variables. So D4 plus D5 plus D6 plus D7. Next, y is equal to, where will be the logic 1? Its corresponding octal numbers. So its corresponding number is D2. Its corresponding number is D2. And then this one is D3 plus D6, D7. Any one D2 or D3 or D6 or D7, one logic 1 in the input, then its corresponding y is logic 1. And what about z? Z is equal to, here it is corresponding input combination is D1 plus D3 plus D5, D7. D5 plus D7. So this is the simple Boolean function. And then when we see this logic diagram, the logic diagram for that one is, for encoder is, the logic diagram for encoder is, take the D1, D2, D3, D4, D5, D6, D7. So what is the x? Nothing but 4, 5, 6, 7. We can take 4, 5, 6, 7. Which is represented by x, and D2, D3, D6, D7, 2, 3, 6, 7, 2, 3, 6, 7, 6, 7 can be represented here. Another OR gate. It will be represented by y. And 1, 3, 5, 7. 1, 3, 5. This is 5, 7. This is 7. We can take OR gate represented by Z. So in this way we can get the simple encoder circuit. So likewise, in order to get this encoder, for example 8x3 encoder, the first step is, what is the definition of encoder, which converts a decimal like a octal equivalent of input into a binary. So octal nothing but 8 inputs. So define the inputs are 8 and outputs are 3, and give the names for 8 nothing but D0 to D7, and give the variable names for outputs 3 outputs X, Y, Z, and then make the truth table for the input column and output columns. There are 8 inputs D0 to D7. We can make the input columns, and X, Y, Z are the outputs. So then we can prepare the truth table and find out the Boolean function either with the K-map or by inspecting the truth table, and then draw the logic diagram. This is the way to find out a combinational circuit of encoder. Next, in this case, suppose any encoder enabled with the more than one inputs are at a time, are active at a time. In that case, the normal encoder was like confused with that which corresponding output should be enabled. Output should be generated. So in order to avoid that one, we can make a combination circuit based on the priority. If more than one inputs are active high, then based on highest priority of the input active element, then its corresponding output will be generated. If you see this priority encoder, and that is the problem definition, and also the priority encoder is let us consider in the design steps. The first step is priority encoder for 4x2 encoder. If you want to design a priority encoder of 4x2 encoder, and then defining the 4 inputs and 2 outputs, and then give the names for 4 inputs nothing but D0 to D3, and its output names are X, Y, Z. And the 4th step is make the truth table. 5th step is Boolean function, and the 6th step is draw the logic diagram. Draw the logic. So first step, we need to design the 4x2 encoder. It's a especially priority encoder. So what is the definition? Priority encoder means whenever the lower element of among 4 inputs is active high, and the immediate higher number are also active high, then we can assign the priority to the higher number, and then its corresponding output will be generated. So based on that, of course it requires 4 inputs, so assigning the values or inputs are 4 and outputs are 2, and also assigning the names are D0 to D3 and outputs are X, Y, Z, and then truth table. Coming to the truth table. So this is the truth table for priority encoder. According to encoder, it has 4 inputs. D3 is the MSB bit and MSB number, and D2, D1, D0 is the LSB number. So X, Y, Z are the outputs. So it is a truth table is a table which gives the relation between input and output. Input and output. So now see that when D3 0, D2 0, D1 0, D0 0, when all are zeros, so it may be whatever it is, maybe X, Y, Z. So irrespective of X, Y, Z, it gives the all zeros. Okay, it gives the all, like its corresponding number is, don't care with the zeros. If suppose D0 is active high, when D0 is active high, so it is the least number. So more than that, less than that, D0 is not there in the list. So this is the number is active high is a D0, and also its highest priority is also D0. So its corresponding number is 0, 0, 1. 0, 0, 1. And then D3 0, D2 0, D1 is 1, and D3 is don't care. What happened? D0 is don't care. So what does it mean? D0 don't care means, suppose D0 is either 0 or 1. when either 0 or 1, but D1 is 1. So if D0 is 0, D1 1, we can assigning the priority to the D1. Suppose D0 is 1 and D1 is 1, also we can assign the priority D1. So whatever it is, so D1 D0, suppose D1 is 0, D0 1, D1 is D0 is 0, D1 is 1. Its corresponding output is its corresponding binary of 1, 0, 0, 1. Or D1 is 1, D0 is also 1. Again, you will get same output 0, 0, 1 because we are providing priority given to the D1. Whatever the irrespective of D0. So that's why we can take 0, 1 as a don't care. Take the don't care. So its corresponding number is 0, 0. Sorry, in this we can take that it is a priority encoder. Will consider only this column. So 0, 0. Here it is 1 D1 active, priority given to the 1, 0, 1. We will get 0, 1 irrespective of 1. It is a 2-bit, so 2 output and 4 input. And then when D0 is don't care, D1 is don't care, and giving priority to the D2, irrespective of D1 and D0, whatever it is, that this don't cares are 0, 0 means this don't cares are assigned with 0, 0, 0, 1, 1, 0, 1, 1, whatever the combination in the D0, D1. When the highest number D1 is high, then its corresponding number is 1, 0. When D3 is high, whatever this D2, D1, D0, its corresponding number is 1, 1. So likewise, we can make the table for priority encoder of 4x2 encoder, and its corresponding output for XY. The XYs are, where is the logic 1 here? Logic 1, 1. So its corresponding numbers. So here it is mentioned don't care. So by combining all the don't cares, all the possibilities in the don't cares, so 0, 0, 0, 1, all the don't cares you can combining and make the truth table and make the Karnaugh map and minimize the function for x is equal to D2 plus D3. Here it is D2 and D3. So we'll get D2, D3. And y is D1, D2 bar plus D3. So, and draw the logic diagram for D2 plus D3 and y D1, D2 dash plus D3. Then you will get the priority encoder. Now coming to the decoder. So basically the decoder is a combinational circuit which converts n number of inputs into 2 power n output lines. And what are the examples of different types of decoders? The general representation of any decoder is n by 2 power n. N by 2 power n decoder. By substituting n is equal to 1, you will get a 1 by 2 decoder. Substitute n is equal to 2 by 4 decoder, 3 by 8 decoder, 4 by 16 decoder. Likewise, if you substitute n is equal to 1, 2, 3, 4, you will get different kinds of encoders. Let us take a typical decoder which is equal to 3 to 8 decoder. What we discussed earlier, 8 by 3, octal to binary conversion. So which we need to reconstruct, which we need to reverse conversion of those binary information into octal numbers to perform the operations. So basically this kind of conversion, encoding and decode operations are most preferable in communications, most preferable in analog and digital conversion. So this is the simple 3 to 8 decoder, 3 inputs A0, A1, A2 and 8 outputs Y0 to Y7. So it is an example for 3 to 8 decoder. Let us see the truth table for 3 to 8 decoder. So as decoder says that it has 3 inputs and 8 outputs. Let us consider 3 inputs A2, A1, A0 are the 3 inputs and Y0 to Y7 are the 8 outputs. So there are 3 inputs, 8 outputs. The 3 inputs, it is very easy to consider that all combinations of inputs. So because it is also binary information, so we can consider this 0002 111 for all the combinations of among 8. And what is its corresponding output? So decoder says that when any one binary combination of any combination of inputs in the n lines which generates the 2 power n different kinds of distinct distinct outputs are generated. So 000, the inputs are 000. Its corresponding octal number is 0. That means Y0 is active. Remaining all will be zeros. Remaining all outputs are zeros. When input is 001, so its actually equivalent number in octal number is 1. So only Y1 is active, high, remaining all are zeros. Likewise, we can take 010, its corresponding number is 2, so Y2 is active. 0111, its corresponding octal number is 3, so Y3 is active. 100, its corresponding Y4 is active. 101, its corresponding Y5 is only active. 110, Y6 is only active. 111, Y7 is only active. So this is outputs. Now how can we generate the Boolean expression for Y1 to Y7? Y1 is equal to. So is it required to take the K-map for all the 3 variables? No need. By inspecting the table, directly we can write down the Boolean function. So entire column, this Y0 entire column, only one output is high. So directly we can take that number. So this logic 1, its corresponding input Boolean function, its corresponding input minter only is the answer. So Y1 is nothing but A2 bar, A1 bar, A0 bar is the Boolean function for Y0. Similarly, Y1 is nothing but only logic 1 is there in the entire column Y1. So its corresponding combination is minterm is 001. 001 can be represented in variables minterm A2 bar, where bar represents the complement binary value, and there is no complement means 1. A1 bar A1, where A1 means it is logic 1, binary value is 1 means uncomplemented variable A0. Y2, its corresponding Boolean function is, its corresponding minterm is A2 bar A1 A0 bar. Y3, A2 bar A1 A0. Y4, A2 A1 bar A0 bar. Likewise, we can write down the A5, A6, A7. A7 is equal to all are 111. 111 means all are uncomplemented. A2, A1, A0. A2, A1, A0 bar. A2, A1 bar, A0. So likewise, we can write down the Boolean function. Then by seeing these 8 outputs, each output have a simple product term, minterm. Product term can be represented in the logic diagram as AND gates. So it requires 8 AND gates. And corresponding complement, is there any representation of complement variable? We require NOT gates. Let us consider this diagram for this one is A2, A1, A0. This is the diagram. A2 bar, A1 bar, A0 bar, A0 bar. So how to draw the diagram for Y0? Like Y0 first. Y0 means take the all the complement value. A0, A1 bar, A2 bar. Take the AND gate. It is a product of, we can take the AND gate for Y0. Likewise, we can take the diagram. A2 bar, A1 bar, A0 for A1, Y1. 0, 0, 1. Take the AND gate like Y1. 0, 0, 1. 0, 1, 0. 0, 1, 0. You will get Y2. Y3 means 0, 1, 0, 1. Y3. 101. Sorry, 100. 1, 0, 0. You'll get Y4. 101. 1, 0, 1. Y5. 110. 1, 1, 0. Y6. All ones. 1, 1. A0. Sorry. A2, A1, A0. Y7. This is the simple diagram. You need to get the 3 to 8 decoder. Logic diagram. Likewise, we can get the 3 to 8 decoder. And also, with the help of decoder, we can implement any Boolean function. Let us see this example, implementation of full adder using decoder. We know that what is full adder. So the full adder is having it is a combination circuit. It has 3 inputs, A, B, C, 2 outputs, sum and carry. What is the expression for sum? A XOR B. And what is the expression for carry? AB plus BC plus CA. And what are the Boolean functions? What is Boolean function representation for sum is summation of 1 to 4, 7. In the truth table, when we check it, 1 to 4, 7 are the logic ones. And carry, for carry, 3, 5, 6, 7. If you check this truth table for full adder, wherever 3 and 5, 6, 7, its corresponding inputs 3 input 3 combination, input 3, input 5, input 6, input 7 are only logic ones in the carry. So how can we make the implement in this circuit in the decoder? Take the 3 to 8 decoder. Take the 3 to 8 decoder. 3 inputs are X, Y, Z. And how to implement the full adder? What are the minterms corresponding sum output, carry outputs are? Sum output values are 1 to 4, 7. So we will get that one also from here. A, B, C, like X, Y, Z inputs. X, Y, Z, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1. It's corresponding sum and carry. So sum carry. So when we check it, sum is nothing but A, X or B, nothing but exclusive or wherever odd number of ones, that is 1. So 0, odd number of ones in the combination 1, 1, 0, 1, 0, 1. And it's carry. So whenever any 1 plus 1, then only will get carry. So 000 means no carry required. 001 no carry required. 010 no carry required. 011 carry is required. 100 no carry. 101 carry required. And 111 like you will get carry. So where is the logic ones here? Its corresponding number. Logic 1, logic 1, logic 1, logic 1. Its corresponding combinations are 1, 1, 2, 4, 7. That is what I am writing. 1, 2, 4, 7. Like 3, 5. Where is 101? Here it is missing 101. Here also we'll get a 0, 1. So 3, 5, 6, 7. So these are the combinations or outputs or logic 1. So we can have a decoder is the 3 input binary information what the full adder has, and also its outputs are sum has 1, 2, 4, 7 logic combinations. So we can take that 1, 2, 4, 7. It's a octal number 1, 2, 4, 7 connected with OR gate. You will achieve sum, and 3, 5, 6, 7 connected with OR gate you will get C. So in this way we can generate the sum and carry in the by using decoder. And if you want to design higher order decoders, so by using the lower order decoders, we can have a 3 to 8 decoder, enable decoder, and how to generate a 4 by 16 decoder. So take this 3 to 8 decoder, take the 2 3 to 8 decoder and connect the XYZ common for both 3 to 8 decoder, and the extra enable pin is connected with the 4th input. That 4th input directly connected to the lower decoder and connected with the inverter with the upper decoder. So this W is 0 for 8 combinations is 0, and the remaining 8 higher order numbers are that W is 1. Based on that, for W is until W is equal to 0, this 3 to 8 decoder is active and its corresponding outputs generated D0 to D7. When W is 0 for higher order combinations of input in the truth table, so logic 1 for a higher order, so that 1 is connected to this, enable this lower decoder and generate the D8 to D15. This way we can create a higher order decoder with the help of lower order decoder. And finally, I would like to conclude with this encoder and decoder of combination circuits in this subject, which will help to convert from a 2 power n digits into n number of binary information, and at the receiver n number of binary information into 2 power n digits. This is most important application in the communication and analog to digital conversion. Let me conclude with this simple example. In the analog to digital conversion, there is a to D conversion. Input signal is analog, output signal is digital. 10, 10, 10, some kind of series of bits. How to generate this series of bits, binary information in the analog to digital conversion? In a simple example, there are some circuits which generate this. It is a simple analog signal. This analog signal is then converted in passing through the sample and holding circuit. You will get sample, hold, sample, hold, sample, hold, sample, hold. So likewise, you will generate the signal which corresponding discrete signal will generate like this. So likewise, this is one half cycle, positive half cycle, let us consider. So then this signal is equivalent with a number, like this sample and holding outputs is quantized with the corresponding exact samples we will need to convert. That means it is, for example, 1.2 we can equivalent with 1, and 2.2 we can equivalent with 2, and 3.1 we can equivalent with 3. So we can equate with this exact number, that is called quantization. So then whatever it's corresponding, this signal is connected with the encoder. This signal is connected with the encoder. This encoder, which corresponding conversion of what is the input signal sample, its input sample is number is 1, its corresponding binary information is 3 input binary information is 0, 0, 1. Next, what is its corresponding binary information? 1, 0, 1, 0. What is its corresponding binary number is 3, 0, 1, 1. Likewise, we will generate the binary information for corresponding samples. So likewise, we can generate the unlocked digital conversion. Input signal is unlocked. We will generate the binary information that can be transmitted by the channel, and at the receiver we receive this kind of packet of 3-bit inputs. So serially, then by connecting the 3 inputs, it will corresponding conversion to decimal numbers of samples. That decimal numbers are samples passing through the low pass filter, and then will generate the continuous waveform of the unlocked signal. This kind of applications are helpful by using this encoder and decoders. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.